number 2. All right. Okay, that's incoming people seems to have slowed to a trickle. Not quite as packed as yesterday, but thanks everyone for coming. Where's my clicker? There we go. Okay, so I actually wanted to change the title of this slide, of this talk, and I didn't get time to modify the slides, but people who are interested in high availability, the book came out on Tuesday that you should all hear about. Who here's heard of the black swan and the whole concept of black swans in the book by Taleb? So his new book came out, and it's called Anti-Fragility. And it's about basically building systems that when you apply a black swan to them, they still work, right? And that's kind of, I wanted to change this to Netflix anti-fragility architecture, and I think I'll do that going forward, because I've read the first few bits of the book. I pulled it off the Kindle store on Tuesday morning. I read it on the way here. But a really worth, if you're at all interested in this area, some great philosophical discussion about how to build systems that are anti-fragile, meaning that they're actually chaotic enough that they don't become brittle. And what we've got here is a very chaotic kind of system. And there's this sort of natural thing to go clean everything up and make it tidy. And the ops guys like to have everything tidy in particular. And what they're actually doing is making it brittle. So it works fine most of the time, then it breaks really badly. If you let the system be a bit more chaotic, and what we've got here is an architecture that actually looks a little chaotic, you find that it's much more resilient to impacts because they'd only affect a little piece of the system, and the problems don't propagate all the way through. It's like having a large brittle thing, cracks propagate through it, whereas something that's soft, I mean, you can't crack jelly, kind of. Maybe that's the wrong analogy, but anyway. All right. Most of you probably know about Netflix. We're all over the world now. We just launched in the Nordics. That's going very well. We're all over the US, Canada, Latin America, UK and Ireland. And we're launching internationally, on a sort of regular basis as the previous countries we've launched get profitable. We just launch a new one. I'm not going to go over the history of how we got into the cloud. Lots of other talks on that, lots of stuff on SlideShare. And there was a talk yesterday afternoon by Yuri, who's my manager, and Neil Hunt, who's our chief product officer, that went through how Netflix migrated to the cloud, what we were thinking about and how we did that. So pull that up on YouTube when they post it, and that will give you a great background from the managers that run the things on how we got here. So this is my favorite slide for what it's like running on cloud. It's all the things that we don't do. Oops, I went a bit too far. So we provision everything directly. We give the developers root access and the ability to provision, not only the ability, but we make them provision their own systems. So that's the normal way. So you don't have to go have a meeting with IT because you need 500 machines, or you want to run a test with, we ran a benchmark which involved about 400 something machines. We needed them for a few hours, didn't have to go talk to anyone about that, we just did it. So it's good to tidy up after yourself. So some things we do, I'm just going to go through the audience here. Who doesn't like putting their hand up? Okay, we've got a few of you. All right, so I'll discount those. Who's using big data Hadoop in production today? All right. Amazon Cloud, hopefully a larger proportion of you given where we are today. APM, Application Performance Management, right? If you don't know what this means, you're probably not doing it, by the way. Integrated DevOps stuff, okay, we've got a few of you. So this tends to be the same hands going up, of course. Continuous integration, continuous delivery, yep, got a few of you. NoSQL, globally distributed NoSQL. Whoa, we've got a few of you doing that too, cool. Platform as a service, as microservices, lots and lots of little services. Yep, not that many. Social coding, who's pulling code from GitHub into production that they wrote? So a few of you, right. So this is when Netflix did all these things in production, and there was a whole story about how we got to doing all of these things. But this is kind of the state of the art, I think, in terms of engineering buzzwords or whatever, the marketing buzzwords. And we've got most of these running in production now. So I'm going to talk about how we put all this together to make a highly available architecture. So I'm going to go through the architecture itself, then basically try to come up with a taxonomy of service outages, dig into a little bit about Well, there's different ways that things can go wrong. So you want to have labels that identify, okay, yeah, we're covered for this kind of problem, but not for this kind of problem. So I'll talk a bit about that. Then I'm going to look at some actual outages from several different cloud vendors, which illustrate those types of outages. And then look at what you can do about it, and what in particular, as people that build applications on top of the cloud, which is kind of my approach, where most of us probably are, how can you learn from these patterns and the things that went wrong so you don't end up making the same mistake? And then finally, a little bit at the end on the components that we have open sourced. We have an open source platform that, if you follow the Netflix OSS Twitter feed, the only thing on that feed is announcements about that platform, the actual products, the pieces of the platform itself. So we have a collection of what looks a bit like random open source projects, but they are forming a platform. And as we get further down the road, probably early next year, it'll be almost like a one-click install to go boot this into an Amazon account. That's kind of where we're trying to get to with it. And then you'll be able to just drop your WAR files in it and go write some code. So what's the inspiration for this kind of architecture? Well, this is one of the fundamental papers in this area. Back in 2003, they were talking about, so what is it that Google did that was different? And what happened was they built an extremely reliable service out of low-cost commodity components and moved all the complexity into the software, where the cost doesn't really scale. The other alternative is to buy ever more high-end, redundant, sort of mainframey style bits of hardware and go vertical. So this was one of the early times where somebody clearly said, no, we're going to stop building systems where you're trying to make a massive SAN highly available on a massive pile of big machines, and you're going to go for low-end stuff and software. So what we're trying to build here is what I'm going to talk about here is a platform and service patterns, which you could implement on any platform, that provide highly available services, but without requiring that the other parts of your service are dependable or of highly available. And the platform isn't highly available, and the infrastructure isn't highly available. So you just assume, and this is echoed in the keynote this morning, you take all of these pieces that you don't have to, if you don't depend on them, but you can still build a highly available service on top of that. Okay, so this architecture does apply to any kind of system. It's just easier to implement on cloud, and we built all the automation around it. You could do it in the data center. It's just hard work and takes longer. So this is how Netflix works. You have the front end, a very high level, just to get context here. So you have the blue box is the thing you have at home, PS3, a digital TV set, your laptop, something like that. And you decide you want to watch movies, so you pull up the Netflix application or the website. So that browse, that's the first box here. You go to browse. You're talking to an ELB with a bunch of instances behind it. Behind that's all the user data for you, that describes you and what movies you like, and all the personalization algorithms that then figure out what list of movies to show you. So now you're staring at a screen with 50 or 100 or 1,000 movies that you can scroll around and pick something, or TV shows. Next thing you do is pick one of those and hit the play button. That talks to a different API that gives you the route to that data on the CDN. It gives you the DRM key that decodes that movie, and it starts logging your quality of service. So this is tracking everything that you're doing. The backend for this quality of service logging system is a single Cassandra cluster doing more than 1 million requests a second. There'll be a talk about that a little bit later this afternoon. So we do, and to some extent, you could say that Netflix is an application for writing log files that occasionally shows people movies. And we're trying to keep you don't really need to log all this data, but we keep having to go back and clean stuff up. Then the client has now been given a bunch of URLs that point at our CDN boxes. So all the gray boxes here are Amazon services, and there's no connection to the data center anywhere in this flow, right? There was a connection to data center when you first sign up, where we store your credit card and do billing and stuff, but that's currently the only thing that really touches the data center. But we touch these Open Connect CDN boxes and the commercial CDNs. And just to be really clear, these aren't running on the Amazon cloud. These are distributed much more widely. They're in ISPs, peering points. They're scattered all over the world. And they are just huge static web servers. They have 100 terabytes of disk, and they have lots of copies of the movies and TV shows you want to watch. And you just point at them, and it's a static web server. It's just HTTP GET. We stream the bits out. That's it. There's nothing clever here. It's just a box with 10 gigabits of bandwidth and 100 terabytes in it. We ship large numbers of those to all over the world, and we've open sourced the design for this. So if you're trying to build a CDN, and that sounds like an interesting box, we've actually published the hardware specs and the software specs. So that's our distributed CDN. Behind that, though, is a bunch of Amazon-based services which put data into that, manage the health of them, monitor and figure out which box has bandwidth on it, record which piece of content is on which box. If you want to watch season 4, episode 6 of Friends or something, it'll be on this box over here, right? That kind of thing. We need to have all that data. And then at the bottom here, there was a talk yesterday by Kevin McEntee, who's the VP engineering that actually led a lot of the initial cloud development. He now runs the content encoding side for Netflix. And if you want to know more about content encoding, there's an entire talk that was run yesterday. So look that up on the YouTube channel. So this is what hitting the website really looks like. It's not just hitting a couple of gray boxes. It's hitting lots of little green boxes, which are mostly the Java ones, and some gray boxes that are things like memcached here. And just to load the home page, you hit all these different things. This is where it looks messy, but what we've really got here is an extremely resilient architecture, because any one developer is building one of these boxes. That's their job. They have a REST API coming in, they call a bunch of other things behind it, Cassandra or REST or memcached, and they're just responsible for that one piece. So if they ship some code that breaks for some reason, like this, we've lost one little piece, right? So maybe one of the rows on your website no longer appears. We no longer know how to do similar movies, or we no longer know how to do your top 10, but the rest of the site still works, right? So that's one of the ways that you get resilience. I'll talk a little bit more about that later. This box in the bottom left that's got everything talking to it is the thing that chooses those lists of movies for you. So if you've ever wondered why you get 20th century movies with a strong female lead and set in China with dogs in or something, you can tag together arbitrarily complicated genres and find those for people. So that's kind of what that core system does. And I've been at Netflix about 5 or 6 years, and at some point I actually was managing the development of effectively that box for the first few years that I was at Netflix. And then we moved that whole architecture to the cloud about 3 years ago, and that's when I moved into this new role as more of a cloud architect, more of an overview of the system. And then some of these back-end things are Cassandra. They're just another Java process that you happen to call. And some of them are memcached or S3 buckets or whatever. Right. So if this is just for the web view, right? So we've got lots of things calling into this architecture from lots of different directions. And that looks a bit more like this. And this is a simplified version, actually, I took from our test account, because the one in production just looks like all the lines are just a big blob. At least you can see some of the calls on this. And I just wanted a diagram that I could repeat. And you'll see this come up a lot more later. So the Chaos Monkey is a little service that we build that kills individual instances to make sure that we can handle killing them. So Chaos Monkey may kill one of these, or you may ship some bad code. It's basically the same problem. And the system can survive that. So if we take 3 copies of that mess of interconnected services and put them in launch each one of them in a different availability zone, and that's a one-click operation. You just tell Amazon, please distribute this autoscale group across these 3 zones. So it's a boom, Asgard just does that. Then I've got 3 copies of everything, and I have an ELB at the front, at the top of this diagram, which is sending traffic into that. So multiple load balancers. So there's a front end for each of the different APIs and websites and things like that. So we have multiple ELBs connecting into this mesh of interconnected services. These services are all stateless, mostly stateless. The ones that have state are the memcached and Cassandra. So I've sort of drawn them at the bottom of this. And that's where the cross-zone replication mostly happens. So if you write data into one zone, you also want to make sure that data is copied to the other two zones, because the next request could go to that zone and want to see a copy of that data. So we have a layer called EV cache, which runs over the top of memcached that basically does that cross-zone replication, and it reads from the local zone and writes to all three. It's just a client-side layer wrapper that sits on top of memcached. And then Cassandra does the replication for us if you want something durable. Memcached, we don't really guarantee any particular consistency or availability, but we have the Cassandra layer for stuff that actually matters. So things like session state are typically in memcached. Things like your personal preferences about things would be in Cassandra. So Chaos Gorilla is another tool we've built. This shuts down an entire zone to basically test to make sure everything works. The response to anything that takes out a whole zone or a large chunk of a zone is to turn off the traffic to that zone. Right? So we've just got this extra little shutdown there. And then we continue to run on two zones. And in several of the recent outages that have happened, we've just run on two zones for a few days, and then when everything sort of calmed down, we just turn back on the other zone. The other thing Chaos Gorilla can do is move zones. So for example, sometimes one of the zones gets too full because there's too many customers going into it, and we're a fairly big customer, so we need some headroom. And Amazon says, could you just move all of your stuff from like zone A to zone E, because we built this new zone E and it's got lots of new stuff in it. So one of the things we do with Chaos Gorilla is it programmatically, systematically takes everything in a zone and moves it to another zone. We did it by hand a few times, and it was so error-prone, and we almost took the site down by pushing the wrong buttons. So the automation here is really important. So next thing. We have persistence at the bottom that's triple replicated. So all my data is in 3 different zones. It's in 3 different buildings, effectively. They're a millisecond apart, a few miles apart. Pretty hard to take them all out at once. And however, if I'm doing maintenance on Cassandra, like I want to upgrade the version of Cassandra, I pick one Cassandra instance which has one of those triple replicas, and I take it out of service so that I can do a software update or something like that. So I'm just taking one node out of my large Cassandra cluster out of service. So that means that that local zone, if it wants that particular replica of the data, it's no longer there. So it's pretty straightforward. You just go get the data from another zone. So our Cassandra tier is typically the one that goes cross-zone more often than the regular services. Now, when we went to Europe, we decided that we were going to eventually do more and more of Europe, so we wanted to create our own standalone infrastructure there. It also gets busy at a different time of the day to the US, so we wanted to try and auto-scale it separately. And it's a smaller system that we could scale up. So we decided to deploy an entire copy of our infrastructure into Europe, and that was quite a lot of engineering work to do that. You can talk to Ruslan here about how that went. He led that overall project for getting everything coordinated to do that. But we brought up Cassandra with 3 more copies of the data for some of our databases, sort of membership databases, things like that. The really write-intense databases we don't typically replicate, but they're storing things like logging information that you don't need to replicate. And then we have this link between them that basically keeps the 2 sides consistent, but it does it asynchronously. So it's maybe a few hundred milliseconds propagation delay before the thing you changed in the US turns up in Europe. And that works fairly well for us. So one of the things that can go wrong there is that the connection, this is over the public internet, just with a TLS type protection. It's secure. It's a secure link, but it's over the public network. This is, you could lose the connection. But when that comes back, Cassandra automatically just connects everything back up, resyncs, and whoever wrote last wins. So that's how everything stays in sync, and it's very automated. You don't have to do much manual work on this. If you lose an entire region for some reason, the other region just keeps running. So anytime that we've had, we put a bug in and we broke DNS or something like that, and we lost everything that could go to that region, the other side's still coming up. And the biggest cause of region outages, I think, is actually getting somebody typing the wrong thing into a DNS config. It's not that the site went down or you lost power. It's one of those central things like DNS. So just to go through those failure modes. Application failure is the most likely thing to happen. We've got an automatic degraded response built in. I'll talk more about that later. Region failure is pretty unlikely to happen. And when it does, it tends to be short duration, and we found that waiting for the region to recover is our current strategy for dealing with that. Zone failure, we basically treat that as something that is going to happen occasionally. And you can roll up all different kinds of failures into a zone failure and just put a box around it and say, if anything goes wrong in this zone, I don't care what's gone wrong, I'm just going to shut it down, run on 2 more zones. So we have a good strategy for that. Our data centers also caused a bunch of failures, connections to it, Oracle dying and things like that. So we still have those systems in the back end, and we still connect to them for a few things. But what we've done is, over time, reduce the dependencies into our data center, and we've got more and more available as we've become less dependent on sort of the single source of failure type systems in the data center and the connectivity to the data center. It turns out it's much easier to build a highly available architecture on a widely replicated cloud platform than to actually do that in a data center. And we've got like failover and systems in the data center, but it's not really a 24/7 kind of environment. Data store failure. What I mean by that is that we ship, let's say we do a buggy version of Cassandra for some reason and it starts corrupting data. We haven't actually had that in production, but you have to guard against the things that might happen. Or somebody just accidentally deletes a key space. Whoops. Yeah, it would be nice to have that stuff. So we do backups continuously into S3. We do a daily snapshot and we do an incremental backup. So anything that's written into Cassandra within 10 minutes or a few minutes, there's a copy of it in S3. If S3 fails, which is unlikely, or we get some account level compromise type problem, we actually have a copy of the data on a different S3 account. So a different Amazon account, right, in a different region. So we copy all our East Coast data to the West Coast and put it in a different Amazon account where nobody else knows the password, different keys, and you can only write to it. And it's versioned so you can't overwrite it. And it has that policy set up to automatically expire the data after 90 days or whatever we felt like. So we have a remote archive. And then, of course, well, if S3 fails, well, there's other cloud vendors providing S3 alternatives, some of them quite cheaply, increasingly cheaply over recent days, that you can store an additional copy in. So, application code fails. You want to be able to deal with it. So you want to run what you wrote. You want rapid detection and rapid response. So run what you wrote means that developers are responsible for failures. They learn, they write code that doesn't fail. They are on call. There's a PagerDuty rota with the developers that deployed the code in it. And the escalation path goes to their management and on the way up. So, if you don't answer the call, your manager probably gets the next call, or at least a coworker does. Use incident reviews to find gaps to fix rather than assign blame. And then there's a few other things that just helpful hints, like keeping timeouts as short as possible, failing fast. If something doesn't work, retrying it, it's probably still not going to work. And waiting longer for it to work is probably still not going to work. So particularly for connection timeouts, don't keep connecting to the same thing and assuming. It's like one of those definitions of insanity. You get the same thing over and over again. You're expecting a different outcome. Just connect to somewhere else and try again, and then give up and propagate the failure up the system. And then we have this dynamic configuration options. You want to be able to tweak timeouts, retries, properties for turning features on and off. You want to do all that in real time. You don't want to have to do it by pushing code. Or editing stuff or logging into a box. So we have, Archias is a global property management system that is distributed globally and has scoping rules. So I can say, change this property for every machine of this application service type in this zone, or in this region, or just that one, or globally, or whatever, right? And the feature we discover it needs is it needs to remember what the previous version of everything was, but we'll get to that. Another thing we announced a few days ago is the Hystrix circuit breaker design. So this is a pattern where you're a developer, you import all of these jar files that are the client libraries for all these other services, but you don't really trust them. Like, they might give you the wrong answer, they might time out. So instead of just calling the code, you wrap it in a circuit breaker, and you call it you fork off a separate thread to call this library, and you sit and look at it suspiciously, and you time it out. And if it fails, you call some workaround that basically says, I have a fallback position. I maybe have a local cached copy to fall back to of something that's maybe less good, but is still okay. Like we do progressively depersonalize the website this way. So instead of getting every possible best recommendation you could get, we gradually fall back to a non-personalized site. But if you call this thing 2 or 3 times and it breaks every time, eventually you flip the circuit breaker and say, I'm just going to stop calling it. And at that point, that's what the circuit breaker pattern does. And then every now and again, you call it again to see if it's recovered. So that's the basic pattern, and this is the flowchart for it, which I won't go through. Lots of detail. So if you're using Java and you think this is an interesting pattern, the client library's there. There's a client. So there's a user interface for monitoring this with a 1-second update. So you can see in real time which circuit breakers are set, which ones are clear. And that way, when you push code and you break something, you can see in a few seconds that it broke. And then when you fix it by making a change or switching the code back, you can see that it fixed in a few seconds. So that's the key thing here. We built this for our API. We're now deploying this across many more of our services. Very powerful. The UI part is coming soon. It's not quite there yet, to the open source thing. Chaos Monkey, there's a talk at the end of today about this, so I'll go over it really quickly. Everything's going to randomly die, so you should help it on its way to make sure your error code handling path works properly. That's basically the idea. And we have Latency Monkey, because just dying is too clean a failure. You want to be able to inject Byzantine error rates and error codes and occasionally be really slow and things like that. Another tool we have is a configuration history tool, which is called Edda. Edda is something like the stories of the Norse gods or something, and Asgard is the same team that did Asgard, and all of their stuff is based on Norse gods for some reason. Internally, it was called entry points, so some of my previous presentations, you'll find entry points mentioned. So this is now out there, it's open source. It's a database which collects the state of your universe in the cloud. It's like it basically continuously scrapes all those describe calls that describe instance, describe ASG, describe EIP, all of those things, pulls all that data and just logs it. As the JSON object that came back from Amazon is put into a MongoDB database, because that's what MongoDB is really good for, and then it's cross-indexed. So now you don't have to say, oh, because somebody says, hey, what's the IP address? I've got an IP address. Which machine was that? Currently, you have to go and scan everything you've got. And when you've got 10,000 machines, it takes too long. So with this, it's a query lookup. It's an indexed field in these objects. So that's the Amazon instances feeding in. But we also have our own Eureka, which is our service registry that's collecting all the information about our entities. Like, this isn't just an instance. It's an instance of our API front end. And this is a middle-tier personalization server. And here's a similar service. So now we know all of those and when they could push code and what version they're on and all those kinds of things, because they all have descriptions as well. So we pull all of that metadata out of Eureka and we store that in Edda as well. And then App Dynamics, which is how I was drawing those little diagrams earlier that showed everything calling everything, that captures the request flow through our system. And they have an API and they have JSON objects, so we start collecting that. Now you can form queries that says who was calling what and what's going on. So that all sounds cool, and it's a very useful tool. But there's one extra thing that makes this really clever, which is that it doesn't just tell you what's going on now, it remembers the complete history of the state. This is a really this sort of very fundamental thing. It means I can say exactly what was the entire state of my machine at any point in the history. Like, what was the state of my infrastructure? You can't do that in data centers. There's no way you could say exactly what was the state of my data center, 4 weeks ago on Thursday night. You maybe know where a few things are, but there's nothing there. Here I can do a query and know exactly what was there. So, and this is what the monkeys run against. Most of the monkeys that we've built are queries against this database that do things like, well, here's something that hasn't been used for a week, I can clean it up. So the janitor monkey, for example, does cleanups by using the time-based part of this. If you want to hear about all the monkeys, it's like 4 o'clock today, I think. So here's a couple of query examples. It's a REST-based user interface with a query syntax. So the first one basically says, hey, who's had this public IP address since the beginning of time? And it gives you a list of instances. That's an old JSON list, right? Show who changed this security group and what was the last change to it? Okay, so I eliminated a bunch of stuff, but it basically gives you this diff syntax on the IP ranges of a security group. Okay? So now I'm able to debug my infrastructure. So in terms of trying to keep everything up and running, because I now know the full state of it, you can go do that. I gave a talk a few weeks ago to a group and saw one of the guys here, and he said, we're already up and running with this thing. And it's pluggable. You can add your own data sources to it. So if you have infrastructure or some other data source, write the code, contribute it, and we'll add more data sources to this. This has only been out for a few weeks, but I think it's a really interesting service. It's written in Scala, so yeah, it runs in a Tomcat server like all of our other stuff, but yeah, for some reason, the engineer decided he wanted to write it in Scala instead of Java. Okay, so we have this distributed operational model. There was a talk a little bit earlier today about this from Jeremy Edberg, where developers are provisioning and running their own code in production. They're on call, they're on PagerDuty, and they use autoscalers because the peak traffic for us is about 7 p.m. on a Sunday night. That's when all of you are watching movies, or all your kids are watching movies. And that's when we're trying to sit down and have dinner or watch a movie, right? We don't want to be sitting there going, oh, we need 4 new machines here. So the autoscalers take care of these peaks, and it runs on autopilot through the weekend, and it just scales up to whatever it needs to be at. And then our DevOps approach is the DevOps teams are building the tooling to run this service rather than actually touching it themselves. You're building automation, you're constraining the developers to use your automation, so you've got more responsibility on developers, but they have a lot of tooling, so they're not getting buried in that. We do rapid rollback, so we push code. Actually, this was demoed this morning. So if you saw the keynote, you saw several examples of the red-black deployment thing. This is what Werner was talking about. So I'll skip this. I'm going to get short on time, talk about some more things. This is what the demo that you saw with the Amazon console. This is our version of that demo. You click there, you're done. It's much simpler. There's no these like tick boxes and lists of instances. And this will work with 10,000 machines instead of having to do 1 instance at a time kind of stuff. So this is a much nicer way of doing the demo that Matt showed you earlier today. So just do versioning on ASGs. So I'm going to now talk about different kinds of outages and give them names so that we can start talking about, oh, this was that kind of outage, this was this kind of outage, I'm covered for them, I'm not covered for them, those kinds of things. So these are the main failure modes that a zone has. And so I've been talking about the code level problems that we have and how we address those. Now I'm going one level below to the platform level. So let's say a zone fails for some reason. Power outage, okay, that's a nice, clean, easy one. Those instances are now off. Any state they had is now gone. When it comes back up, they may be still there, but you probably just delete them and start again, right? So that's a much easier. It kind of sounds bad, but it's actually the easiest kind of outage to deal with because it's a very clean outage. When you try and route traffic to a machine that is down, you get no route to host, right? Host isn't there anymore. So you get a fast fail. So it's a clean break, a fast fail, and it's relatively easy to recover from because you just power them back up again, and you're back again, right? So the next kind of outage is a network outage, where the route into the system goes. So let's say all the perimeters for this particular zone are no longer working. But the machines inside are still working. They're still running. They're still talking to each other, going, oh, why isn't anyone talking to us? They're still in there. Cron jobs are running. Things like that are happening. But it doesn't tend to happen like that. It tends to happen kind of like this. Randomly, flickers on and off. So you get odd things happening, and it's hard to deal with. And when when you get a network outage like this, quite often there is still a route to that host, it's just not responding. So packets are being dropped. So you tend to get long timeouts. So it's very different to a power outage where you maybe get just no route to host and a fast fail. This is a slow fail. You back up, all your threads clog up, and the system will sort of grind to a halt, and then it flickers on and off, so it's hard to tell what's going on. So it's a much harder type of outage to deal with. Finally, you get these, what I call a zone-dependent service outage. This is the sort of EBS, ELB, SQS, S3, something like that is broken, or maybe one of your own internal services, like our discovery service, or something like that, or a Zookeeper server, is down in that region, in that zone, sorry. And what happens is that outage ripples through into the rest of the system in a fairly complex way, which tends to be very hard to debug. It's not immediately obvious what's going on. There we go. So this is just a summary of those types of outages for people that are reading these slide decks rather than listening to me. So let's look at regional failure modes, sort of going up one level. One is a regional network outage. This is kind of the DNS failure. If like all of your traffic into a zone is like .netflix.com or something, and somebody manages to mess that up, then you cannot get there. So that's, or or the routing is broken. There have been times where there was a black hole route where no outbound traffic could get out of a zone, get out of the entire region for a short while. So those are the kinds of outages that take everything out. The other kind of outage is control plane overload. This is one of the more complex ones. So in this case, because of an outage, like a power outage, then the systems are trying to recover from that, but there's now a lot more activity, and it overloads the ability to control that service in that zone. And that inability to control that service spreads through the control plane and starts affecting other zones. So this is a regional outage, which is really because of a local outage that is propagated with a kind of a cascading failure. So typically what happens is after a little while it catches up with itself, and the multi-region part, the multi-zone part of the outage goes away. So we've seen this a number of times where there's a power outage or something, and it spreads across the regions for a little while and then gets back, and now it's kind of working okay. But you've still got the original outage there, but it's no longer a regional one. And then when you clear that, everything gets better, right? So these are much more complex to diagnose, and I'll talk a bit later about what's been done to fix these. So that's just to summarize that. And then global failure modes. This is generally self-inflicted. It's pretty hard to actually break the global cloud, but we do this with like global property changes that go wrong, or bugs, or memory leaks, so you deploy everything, or more famously, time-related things like leap seconds and leap years tend to have this outage, and I'll go a bit more later. So, and finally, if you have this great idea that when you lose a zone, you're going to send all your traffic to the other zone, but that zone doesn't actually have enough machines running in it to take that traffic because you were running pretty hot and you didn't auto-scale up fast, then that one goes down too. And now you do this. And then someone thought it was a really good idea that if the US is down, you should send all the traffic somewhere else because that global failure would be better and that would be a really good idea. So then you do this, and then you have nothing left, and everything's down, and turns out that was a really bad idea. So migrating demand across regions is something you have to do extremely carefully. We're actually looking into the ability to do cross-regional failover, but we're going to be very careful to watch out for this kind of scenario. And we may get it wrong a few times. But this is, it isn't as simple as saying, oh, I'll just send more traffic over there. You've got to make sure you can handle it when it gets there. Okay. So let's look at some actual outages. Here's some global software bug outages. Looking at the global level, S3 had an outage in 2008. They fixed it. They haven't had an outage since. But again, this was a gossip protocol problem, like a metadata problem that propagated globally. Azure had a leap day outage this year where they were making certificates that lasted for a year. So they wanted the end date of the certificate to be 1 year in the future. So they tried to make certificates that were valid until the 29th of February 2013, and that day doesn't exist because it's not a leap year. So it failed, and then because they had no certificates, their entire system globally sort of collapsed because they could no longer talk between different parts of their system. So that's a one-line code bug, right? And it was a one-line fix. And so how many one-line code bugs do you have like that? Probably in your code and in everywhere else. So not to point the finger at them particularly because there are probably other instances of this lying around. It's a really good example. And this configuration error that we had this year, somebody updated something which globally broke Netflix. And then after about an hour, we figured out what was going wrong and switched it back, and then we fixed it. And what we learned from that was that we want to keep all of these global properties. We want to keep the history of those properties, so we should store them in Edda. And we weren't currently doing that. So that's a kind of a future enhancement. So then I can go back and look at the history of every global property that we've ever had set. Looking at regional control plane overload, there was this EBS outage in April of last year. And this was human error, cascading failures, the usual kind of things. The impact on Netflix was that all of the instances in one zone basically started to hang. We couldn't launch replacements because we use an EBS-backed root disk, but it didn't affect the data integrity. And we have a few MySQL master slaves, and we actually lost some of our slaves, but the masters were okay because it happened to hit the right zone for us to just hit the slaves. So it wasn't too much of a deal. And our MySQL stuff is generally not customer-facing, it's optional functionality. So this was slightly higher errors, slightly higher latency, no big deal. I could tweet, hey, Netflix is still up. I think this was, maybe this was when, there was a case where Jeremy was still at Reddit, and he was sitting at Reddit complaining about the fact that Reddit was down and watching Netflix movies. So that's kind of, we need to stay up so that when everyone else is down, they've got something to do. It's very important. Like we have to stay up during Hurricane Sandy so that your kids don't drive you crazy while they're at home because the schools are shut, those kinds of things. A regional network failure, Google App Engine had one of these a few months ago, which was a network router that overloaded and it cascaded and it just kept cascading and it basically shut down all traffic through their system, or it had about a 50% error rate for a few hours. You know, the workaround for that is just be really careful about having enough capacity, and particularly when you're performing maintenance operations. I mean, this previous outage was actually a maintenance operation that triggered it. And if you're running infrastructure, you know that's the most dangerous time. More automation helps. Zone power failures is this June's big storm. You know, they lost one data center. It was 7% of the US East capacity. It wasn't like US East went down. It was 7% of it for 10 minutes. I mean, that was the actual outage. But the ripples out from that caused a bigger problem. We lost about 20% of traffic for a few hours. So we weren't completely down, but we had a partial outage. And so it's kind of, you can say, well, we went down, but it wasn't perfect, right? But it was a relatively small impact, and I'll show you what actually happened. So there's the power outage. Now we have a Eureka as our service registry, and due to a bug in the way that was configured, the service registry didn't mark down the bad instances that had gone away. It still listed them as available. So every request that came in potentially could call us a machine that was no longer there, and it would just time out and take a long time. And there was like 1/3 chance that anything you tried to call was broken. And then what we also had was a bunch of applications in our infrastructure that weren't using zone-aware routing. They were calling across all zones rather than calling inside their zone, right? And this shows the danger of doing that. It makes you can kind of think, well, what if there aren't any left in my zone? Well, we have an algorithm that says if you can't find any, then you call cross-zone. But anyway, and what the fix for this was pretty obvious. We turned on zone-aware routing as default. It was available as an option, but not everyone had picked it up. So we flipped that option around to make it the default going forwards. Did a bit of debug and work for the people that weren't using it to make sure that was okay. And we fixed the configuration in Eureka to make sure that it kind of had a fail-safe mode that got triggered. It says, I'm not sure what's going on. Too much stuff has disappeared at once. I don't want to just shut everything down, which is actually a useful fail-safe mode. But you have to be very careful how you trigger those and make sure you're aware that it's in that mode. And it took us a while to figure that out. All right, and then some dependent service failures. Again, this is like going back to that big storm. EBS goes out, the block store, that takes out the ability to launch instances, that takes out instances that are actually part of the ELB service, the load balancer service, and now the load balancer is impacted, and now I can't manage my load balancers, and we have a network outage, right? So because we can't get the traffic through, and we can't manage that. And AWS in their report talked about what they were doing to fix that, and this is a very useful pattern. So what they've done is, instead of having one command queue for their control plane, they now have a command queue per region, per zone, and then they have a global one per region that is just about the routing. So requests which are to turn on and off individual zones now go to their own queue that are modifying the DNS records at the top. So that's that top one. So now you can control traffic routing, and there will never be an overload of traffic to that because the instances aren't involved in sending commands to that. And then in each zone, they now have a separate queue, and all of the activity involved in trying to recover from an outage in one zone just builds up a queue of work to do in that zone, and all of the other zones that aren't affected have empty queues and will take requests, and you can manage them. So think of this pattern when you're building your own systems. When you've got a distributed control system, make sure you don't have a global command queue. I mean, you want to be able to send commands to it, but you want to have sub-queues. And you want to be very careful about the failure modes of that. So this kind of hardening is, I think, in place now. They've been working for the last few months to implement this for some various AWS services, and it's described in their outage report. So, yeah, this is kind of one of the things about AWS. They learn from the problems they've had, and they tend to not recur, and they figure out how to fix them, and they've been working through. So it's becoming a much more resilient system as they learn all of these kinds of failure modes. All right. I'm going to skip through this section pretty quickly because there's a talk up next for Cassandra from Ruslan and Greg. So this is what our service pattern looks like for all of our REST clients talking to a REST data provider service in the middle there. And then off on the top right, you have a Cassandra cluster that is just serving one kind of data to one kind of consumer. So we've fully denormalized our data model. We have 50 different clusters. We're doing, the biggest one's doing like 1 million reads and writes a second, something like that. And then at the bottom, this data center this data provider service can actually handle the replication into the data center or sucking data from it, maintaining that kind of eventual consistency to your legacy systems that you typically have to do. So this is what our microservices look like. You're basically dropping code into a Tomcat server. This is our standard, instance. It's a base AMI. We have a bakery. It builds on this. We have Asternax, which is a Java client library, which has a bunch of better resilience options for finding machines that are, avoiding machines that are slow, and for retrying better, having a better retry algorithm for when things go down. This is what the code looks like. I'll skip past this. And then this is what the Cassandra instances look like. And I wanted to really make this clear. We're using the internal disks in these instances. We don't have attached data. We're not using network attached data with Cassandra. You're already using all the network traffic just to get to the Cassandra instance. And you already have 3 copies of the data. So you are using local instance storage. And that makes Cassandra incredibly cheap as a storage engine. And the new mega machine that they just came out with today with 48 terabytes of disk in one instance, we have to benchmark that to see what happens. But that is an incredibly cheap way of storing stuff because you're using the internal. And if you're trying to do that yourself, this is the best pattern for doing that because you don't ever want to lose that instance and lose all the data that was in it. Cassandra handles the replication, so I've always got 3 copies of this data, and I can put data in it very rapidly. So we've been using the 1.6 terabytes of local disk store in the M2 4XL mostly. And then recently we've been converting over to the solid state disk instances. And if you've been trying to get hold of solid state disk instances, we're sorry, but we're using them all. And they're gradually getting easier to get. But yeah, we have a few hundred of them, and they are in short supply. But they're gradually becoming, over the next few months, hopefully they'll be more generally available. But 2 terabytes of storage, you can do 1 gigabyte per second to disk and across the network to these instances, 1 gigabyte per second, and you can do 100,000 IOPS. And I just trivially did this with a couple of, without doing any tuning. I just went, I wonder what I can do, ran IOZone on it. Yep, it does 100,000 IOPS, and it does do 1 gigabyte a second. That is a monstrously powerful I/O server. All right. We have automation. By the way, on the left, we still have this Tomcat server running, but it's running Preem. And this is what Preem does. It zero-touch auto-configuration of Cassandra. It's basically as near as you can get to running something like Dynamo, but on your own instances. And this is kind of the model I'd suggest for people. If you're starting out and you're really small, start on Dynamo. If you start to get the proportion of your bill starts to get big, or you start getting to the point where it's worth running, say, 6 or more instances, then you should probably cut over to Cassandra because you'll find that it's a much lower cost, more linear scalability in terms of costing. The per request pricing of Dynamo, it gets a little bit more expensive as you get to the high end of the scale. But at the low end, you can't really run Cassandra clusters that are small enough to be cost effective at the low end, so that's the problem. All right, we do backup, we do growing the thing, and I'll just get through this. So the last piece, this is all an architecture that would be maybe a lot of work to implement, but we're releasing it as open source. So we have it on GitHub, one piece at a time, intros, documentation. And what we found is that the biggest thing we found is that if you start open sourcing your code, it gets cleaned up because the engineers have to write documentation. They realize that the configuration's not that good and that interface isn't quite right, and they wish they'd done something different. And they do all the cleanup work before they open source it. So if you've got technical debt in your code base, and you get this sort of, at the end of it, you're a hero because you've got your open source on GitHub and that makes you feel good. But you actually did some work to get there, and it's the best code cleanup mechanism we've ever found. If you want, we have a booth in the exhibition center. If you want to come through and talk to us, we'd love to know what parts of the Netflix library projects you're using, and what's missing, what you'd like to contribute, those kinds of things. So we're trying to gather together some sense of a community here. There's some mailing lists and things like that, but we're particularly looking for input. This is a list of all the projects. The ones in light green are the ones that are not yet out. And part of the biggest part of this is our bakery, which is a Jenkins-based build system that takes your code, checks it out of GitHub or whatever, and turns it into a baked AMI that you then deploy. There's a few other bits and pieces here that will be along a bit later. The load balancer that we use internally for doing our zone-aware routing between services, that's on the list to come out, and the server-side there's some instrumented patterns in the calling between services that we have coming out soon. And then we also, the build Dynaslaves, this is using the Amazon VPC service to take our current data center-based build system. Our Jenkins system is actually running in our data center because we had to start somewhere. And it dynamically bursts into the cloud and builds new slaves there, build slaves there, and then shuts them down when they're done. Okay, so some more talks. There's a talk coming up soon, although we're running a little late today. You get choice of talking to Jason about security or data science from Kurt Brown. And then this afternoon, Cassandra, I'm on a panel, and then the Chaos Monkey. So hopefully we'll see you again at one of those talks. And this is Techway. Feel free to connect to me on LinkedIn, and I'll be around the conference. I think we're probably out of time for a Q&A, but because there's more talks coming up. But if anyone desperately wants to say something, I'll be here for the next few minutes as we set up. Thanks.